Good morning. We are heading into midterm 2, so we're through chapters 5 through 8. In preparation for midterm 2, you guys have been working on all these homework problems, all the examples from class. And so now what we can do is let's take a look at some midterms that showed up in previous years. We did this for midterm 1. I think it worked pretty well. So let's go back. I've got a couple of midterms. Here's a midterm 2 from, I don't know, 5-6 years ago. And I got a second one of these. So again, I have 2 of these we can go through. Let's take a look. And so same format as before. 4 problems, individual parts A, B, C, D, E, F, G, H, I, J, K, elemental P. And then we can go through and kind of judge. We can make our own determination. How difficult are these? How is the real midterm going to compare? So let's take a look at the first one. Now, this is friction and circular motion going on. Sounds like chapter 5 kind of stuff. It says we have a 3,500 kilogram truck with a 200 kilogram crate going along a curve. Now the curve's level, so there's no banking on this problem. The curve is level, but it's circular motion. And so what happens is, now I'm going to do what I talked about in class as a back view, where the velocity is into the board. Here are the taillights. I didn't draw the license plate. Here's the truck. There's the crate. Now it's specifically the crate that we're looking at. And so there's a normal force, and then there's a gravitational force. Now, there is an acceleration to the right. And so I'm going to need a frictional force to provide for that. I should have got the acceleration drawn. I didn't do that. I'm going to lose points on that for sure. That's not a good start. I do have it drawn down here. So this is a back view. This is a top view. So if I'm up above the truck is going, in this one it's turning to the right, this one is going to the left. Oh no. Anyway, so here's the velocity here. The acceleration is towards the center, and the acceleration will be in the direction, or the static frictional force will be in the direction of the acceleration. That's what we need. We need a static frictional force to push us to the side, and that's what's going to allow us to follow the curve in the road. If we don't have that, then we go straight. So now we need to know what the radius is. Now that's measured from where the object is out to the point that's the center of the circular motion. That's the center of the circular motion. Here is the path that the truck or the crate is following. So the crate is going around in a, now it doesn't have to be a complete circle, but I just drew the circle as a guide to show us, as we go around the curve, we're going to have a radius of r. All right, the radius of the curve of the highway, 50 meters. The crate has a mass of 200 kilograms, and it says that between the truck bed and the crate, there's coefficient of friction of 0.45. Now, I was in favor, when we were moving this crate, of getting out some straps or something to make sure that it was secure. But other people were saying, oh no, the coefficient of static friction is 0.45. If we come to any curves during the move of this crate, we'll just do some quick calculations. But I'm sure that the static friction will be enough as long as we slow down. So we'll see. So let's see what happens here. So we come to a curve in the road, and we go, before we go any better, we better stop and do some calculations. So we say, all right, there's an acceleration. Again, I need an acceleration arrow right there. The acceleration is going to be given completely by the static friction force. N can't do that. mg can't do it because they're in the wrong direction. We need an acceleration that's radial, horizontally, towards the center of the circular motion. So static friction divided by the mass, that will determine how much acceleration we have. Now, the static friction that we actually have available is going to be somewhere between 0 and some maximum value. So what we could do is say that the acceleration that we actually have is going to be less than or equal to this maximum value, the maximum value of static friction will be proportional in our basic friction model. We're treating that as proportional to the normal force. And in lab, we found out that's a pretty good approximation. So we're using a static coefficient of friction times the normal force, and then dividing through by the mass of the crate. When we do that, when we take that, then we can take the normal force and show that the normal force is going to be just as large as mg. We can set n equal to mg. And so with that replacement, the m's cancel. The gravitational mass and the inertial mass, they cancel out. And so the maximum acceleration we could hope for is mu sub s times g. And then we're asking each other, hey, did you really check the coefficient of static friction carefully? Because if it really is a 0.45, then this is saying that we could go around the curve at a speed that would require an acceleration of 4.41 meters per second squared. So the value of static frictional coefficient given would enable the crate to go around the curve at 4.41 meters per second squared. Now, how is that related to the velocity? And for circular motion, we showed that a is to v is v is to r. And that gave us the formula a is equal to v squared over r. And that says that the speed can be related to the radius and the acceleration. Specifically, the radius times the acceleration with a square root. And again, don't forget the square roots. I know it's an easy thing to miss. Check your numbers when you do the problems to see if they seem reasonable. Sometimes that works, sometimes it's more difficult. In any case, putting in the numbers for r and the acceleration says that we should be able to go through the curve up to, at a speed up to, and including, I don't know, then we're right at the critical point where it slips. 14.8 meters per second. So that sounds like 30, 35 miles an hour. So don't go any faster than that. Maybe leave a little bit of margin to make sure that the crate doesn't slide. All right, questions on that? That's a good kind of medium difficulty. It could have been just a bit more challenging. But that falls into the range of medium difficulty, I think. Okay. All right, let's go ahead and move on into question 2. Question 2 says this. Now, this is coming from, I guess, chapter 6, right? This is where we took a closer look at gravity, and we started to look at how gravitational forces and gravitational fields vary with distance. So rather than just look at the surface of the Earth or something, we're looking at longer distances of gravitational effects. So first of all, it says, what would be the gravitational field at the surface of the sun? Now, the surface of the sun is like at 5,800 kelvins. It's a really high temperature environment. I don't know how we get something in there to measure the gravitational field, but I mean, the material that is at the surface of the sun, those outer layers are in a gravitational field pulling them together, and because of their thermal motion, the sun is maintaining its size. If we took away the thermal motion of all of the molecules, the gravitation would collapse the sun, and that's eventually what happens once the sun runs out of fuel for its nuclear reactions, for nuclear fusion. The sun's going to, at that point, the core regions at least will collapse. And so, anyway, let's calculate what the gravitational field would be at the surface of the sun currently. So the gravitational fields are given by big G, big M, over distance squared. And since this is being measured at the surface, let's say that the distance is just the radius of the sun itself. So, so here it is. Here is the sun. Here's the center. The distance out to the surface is r, and so I put that in and squared it. And there's a lot of units going on here. It's always good to check units. Play around with that while you're doing homework problems. And then when you're on a midterm, that will allow you to check your units faster. So practicing looking at all the units can really help catch mistakes. So the newtons have kilograms meters per second squared. The kilograms then have all canceled out. What do we have? I guess we want to just look at the newtons, huh? So let's keep the newtons. And the kilograms don't cancel. That gives me newtons per kilogram. Those are units of gravitational field. And then the meter squared here cancel the meter squared here. Oh, and then that's done. Okay, that wasn't too bad. So the gravitational field is at 275 newtons per kilogram. Now we showed that newtons per kilogram are equivalent to meters per second squared, but typically we're thinking of gravity now as a force. We're almost always going to be working at that in terms of mg. The force of gravity is mg, and for that these units of newtons per kilogram work really well. So that's pretty large, that's like, 20, 30 times larger than the gravitational field at the surface of the Earth. So you think of all that stuff, the solar wind being blasted out into space, all those particles have to be traveling fast enough that they can overcome the gravitational force. So the gravitational force is pretty large. We could go back and ask, and I think we do. Okay, we're headed there. What is the escape velocity from the surface of the sun? So now it's not quite that simple. It says we're going to launch something. We're going to launch something from the surface of the Earth, not the surface of the sun. I think we have another example. We'll come back and think in terms of the surface of the sun. This is from the surface of the Earth. And so we're actually, we have spacecraft here at point A, and what we're trying to do is launch it so that it never comes back. And we talked about that in class as being the escape velocity, which sounds really cool. So the question then becomes, for something sitting on the surface of the Earth, it experiences Earth's gravitational field. It also experiences the gravitational field from the sun. Who's the bigger effect? And as far as the force, it's the Earth. Now the force depends on 1 over r squared. If instead of looking at the gravitational fields and the gravitational forces, what if we think in terms of potential energy? Now in terms of potential energy, that's only divided by r, and that means that the sun's effect might be bigger, right? The sun had a disadvantage in terms of its effect in terms of a force, because we're dividing through by the distance squared, and the sun's so far away. But when we actually carry out the kinetic energies, let's do this. Let's say that we need to launch from point A with a certain kinetic energy. Now, what we learned in Chapter 6 is that the potential energy, the general formulas for gravitational potential energy are negative values. So the potential energies are given by minus gmm over r. And that means that at point A, the plan is to have enough kinetic energy, which is a positive number, to overcome the negative values representing the gravitational potential energy that's holding the object to the surface of the Earth. So we can think of that as a binding energy, something that has to be overcome. So we're going to have a great big positive amount of kinetic energy that exactly balances the negative gravitational potential energies. Now I wrote this, I took these to the other side, and I decided I'm not going to deal with the minus signs on this, I'll just take their absolute values. I know they're both minus. There's a gravitational potential energy due to the sun, and there's a gravitational potential energy due to the Earth. I want to combine those both together. Here are their expressions. So I need enough kinetic energy, 1/2 mv squared, to overcome this much potential energy and this much. Now, the little m's canceled out. I'm ending up with v squared 2 times big G. And here's what it comes down to. this quotient, the mass of the sun divided by its distance, and then the mass of the Earth divided by this distance. Now, if we're launching from the surface of the Earth, we're much closer to the center of the Earth than we are to the center of the sun. So again, this is mass of the sun over distance. So we've got to use, for that, we have to use this. So the sun is that far away, 150 million kilometers, 150 billion meters, but the center of the Earth is here. So this is 6.37 times 10 to the 6th meters. And again, these are all being measured center to center. Now I know there's a little small difference if we're launching from the side of the Earth away from the sun compared with towards, but if you look at these numbers, see how big the Earth-Sun distance is? It's like 150 million. What if I add or subtract 6,000 kilometers from that? And you go, that's not going to show up in my significant figures. Okay, so the effect of the size of the Earth and whether we're launching from the side closer to the sun or farther away, it's a negligible effect. At the level of precision, we're, at 3 significant figures, that's not going to turn up. So we're not even worried about that. So we're just going to say distance to the sun, distance to the center of the Earth. And then what we can do is we can actually, here are the numbers. The sun, 2 times 10 to the 30 kilograms. The Earth, 6 times 10 to the 24. That says that the sun is like 300,000 times as much mass. Now that gives it a gravitational advantage, right? 300,000 times as much mass, isn't that going to create 300,000 times as much force? But it also depends on how far away that is. The center of the sun is 150 billion meters away. That's 10 to the 11th power. The center of the Earth is 6.37, 10 to the 6 meters. Oh, look, these two terms are going to be comparable. And in fact, the sun, the term of gravitational potential energy due to the sun, is actually larger. So what I did was I first of all answered the question, because I wanted to get full credit. So I answered their question and solved for V. Now this number, 43,600 meters per second, that includes both the effect of the sun and the Earth for something launched from the surface of the Earth. Nothing is being launched from the surface of the sun here. We're only looking at way out here where the Earth is located, and what that's saying is the sun's potential energy is still the dominant effect in terms of energy. The way we could represent that, remember the potential energy formula is minus GMM over R. Well, if I plot that, you could treat the gravitational potential energy of the sun as kind of this curved potential energy function showing how it gets deeper and deeper. If I'm out here, I'm not feeling much of the effect of the sun, but as I get closer and closer, I drop really, really low in terms of potential energies. And that will hold me in place, and it's going to be hard to get back out. The Earth is a little blip out here at some distance. So as far as the solar system, the sun is this big funnel effect in terms of gravitational potential energy. And then the individual planets are little blips located at different distances. So the question becomes, how much kinetic energy do I need to get out of this blip of just the Earth? And if I ignore the sun, it says it only takes 11,200 meters per second to get out of the potential energy of the Earth. But then, to additionally get out of the potential energy of the sun requires a much higher launch speed. Now, if I ignore the Earth, if I only include the sun, so let's come out to a place out here in Earth's orbit. So I am still this distance from the sun, but I'm not at Earth anymore. So we launch something out to a space station out here somewhere. From here, I would still need a launch speed of 42,200 meters per second to leave the solar system. So you can see the escape velocity due to the sun versus the Earth at the location of Earth's orbit is still 4 times as large for the sun. Okay, so that's the dominant effect in terms of gravitational potential energy. So yeah, when we launch these satellites out into the deep parts of the solar system, we either have to launch them at really high speeds, or another possibility is that we guide the satellites or the spacecraft past one of the large planet like Jupiter or Saturn or something, and you can actually use what's called a slingshot effect, and you can use those planets to pick up the speed of the spacecraft. So if you guys follow any of these NASA missions out to different planets, you'll know that the slingshot effect has been used over and over to get spacecraft redirected and to pick up their speeds. That way we don't have to build the rockets so big to launch from Earth, as long as we can get them out in the region of these planets. Their gravitational fields can help accelerate them. So it's an interesting effect. All right, moving on to problem 3 here. So here we've got an elevator. So this is what, chapter 5? This is clearly chapters 6 and 8, huh? So this is 6, and then coming back with potential energy in 8. Here we are. Maybe this is 7? Oh no, this is chapter 8 too. So this is 7 and 8, kind of. Elevator cable breaks. 1,300 kilogram elevator drops 30 meters onto a spring. The stiffness of the spring is 90,000 newtons per meter. Calculate the kinetic energy velocity of the elevator at impact with the spring. Find out how much the spring compresses. That's enough to go with now. So here is the elevator dropping. Now that's 30 meters. I didn't draw this to scale. And then here it is when it first makes contact, because they ask about how fast it's going. And then here it is at maximum compression. So at this point, the elevator has been stopped by the forces of the spring. Now, what we should point out, this isn't going to come up in the problem, but what we should point out is, unless there's a damping effect, unless there's something right here, that once the elevator stops, something locks the elevator in place, it's just going to get shot back up the elevator shaft, right? And so if we go from picture A to picture B to picture C, and then we would return to picture B to picture A, the thing will just oscillate back and forth. I mean, it could be a ride at an amusement park where you just keep getting shot back up and then you come back down and hit the spring. These are the numbers that we're given. Let's see if it's an extreme amusement park ride here that we're looking at. Now for the first part, they're just saying how fast are we going here. I'm hoping that's an easy problem at this point, because the midterm's not very far away. For that, we can say the potential energy at A has been completely converted to kinetic energy at point B. That would be mgh equals 1/2 mv squared. Cancel out the m's. V is equal to 2gh to the half, 24.2 meters per second. That's our prediction. Now that's using energy conservation. Now I know from experience what happens with chapters 5, 6, 7, and 8 is, I'm going to say chapters 7 and 8, is that students, sometimes really good students, have really learned everything from chapter 4 and 5 really well, and they kind of think, this energy stuff, I can still do it with chapter 4 and 5. You have to let go of that idea, because there are going to be problems that are going to be either much easier to solve using energy approaches, or some problems where it's going to be almost impossible to use techniques from chapter 4 and 5. Now some of these you could get away with either approach, but I'm going to say start practicing energy techniques on all of these. This specifically is asking about kinetic energies. And so, did I not answer that? I didn't answer it. Oh my gosh. I said that, but then I didn't follow my own advice. So in part A, I need to take mgh and calculate that. So I need to take m, that's 1,300, times g is like 13,000, times 30 13,000, so that's going to be like 390,000. I'm going to guess 390,000 joules. Check that and see if that's right. Oh, I lost points there too. All right, a little discouraging. On part B, it says find the distance of maximum compression of the spring. Now remember, when the spring compresses, that's going to represent an energy of 1/2 kx squared. But when it compresses, it also represents additional gravitational potential energy. By the time the spring is fully compressed, the block has dropped a distance of h plus x. So I can rethink my 0 point for potential energy. I can say that we're dropping all the way h plus x. Now, how far? Oh, we've got to solve for x. Okay, got it. So I'm going to write this as mg h plus x equals 1/2 kx squared. That's looking like a quadratic because I'm solving for x, and I have a term in x squared, a term in x, and I have a constant. So using the quadratic formula, now we've talked about this before, when you solve the quadratic, it's minus b over 2a, so that's mg over k, and then plus or minus b squared minus 4ac square root over k, and I separate the two portions of the quadratic. This was something that a fellow grad student showed me, and some examples of this. Anyway, so this is going to be meaningful. X equals mg over k is equal to 0.142 meters, and then the plus or minus here is 2.918 meters. Now that number is much bigger. Anyway, we're going to take the plus solution, 3.06 meters. That's the amount that it compresses. Now, it turns out in this example, you know how we were talking about when it hits, it could shoot the elevator back up. Another thing that could happen is the elevator could drop, it could hit the top of this, and it could get locked onto the platform. And what that would do then is it would oscillate back and forth. What you can do is you can go through and show that what we solved for here, this would be the equilibrium. That would be the point at which if you took the elevator and just set it on the springs, you didn't drop it, and you found where the equilibrium point is, the equilibrium compression would be at mg over k. So that's kind of interesting. This would be the amplitude of the oscillations. Now we haven't looked at oscillatory motion yet. We'll be getting to that in chapters 14 later in the semester, but this is the amplitude of oscillation around the equilibrium. So that would say that if the elevator hits and it locks onto the platform, maybe there's some really, really good Velcro or something that holds it there, then it would start oscillating, and it would oscillate within what we call an amplitude of 3.06 meters back and forth around the equilibrium point. Okay, so that's A and B, and we had to use a quadratic, so be ready, that could happen. And then part C and D in the problem, let's see. C says, what is the highest velocity that the elevator reaches? And at first you might think, well, isn't this it? Didn't we already solve for the highest velocity? But that's not quite the highest, because it's going to hit the spring, and at least initially, when the elevator hits the spring, the gravitational force will be bigger than the force from the spring. So over at least a short distance, it's going to continue to pick up speed. So it's going to go faster, 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 and it's going to hit that spring, and for a short distance, it will continue to pick up speed, not as fast. What's the crossover point to where the acceleration reverses direction? Where does the acceleration equal 0, and where does it go negative? Well, the acceleration is 0 at a point where kx, I'm going to call this the equilibrium compression. X at equilibrium, k times that, is equal to mg. So this is the equilibrium condition And when we're at equilibrium, the forces will go to 0. And that means the acceleration is 0. And that means the velocity is the highest it's going to get to. So that's the highest value of velocity, is when the acceleration goes to 0. Now, when we solve for this, it turns out to be our old friend mg over k. That's the equilibrium point, and that is at a compression of, it's not much, it's 14 centimeters. So remember, eventually the spring's going to compress 3 meters, but at 14 centimeters of compression, that's where it's going to be traveling the fastest. So now this gets a little tricky, because I don't have a picture. This is point D, and it's somewhere between point B and point C, and the conditions at point D is that x is equal to 0.142 meters. So what we can say is, at point D, we could go back and say that the gravitational potential energy, the amount that this has dropped, is a distance of h plus x equilibrium. And so now I'm going to use that as the distance I've dropped. Now that's going to be the 30 meters plus this extra 0.142. Now at point D, I will have kinetic energy. I cannot ignore, the kinetic energy is here. I've got potential energy in the spring, 1/2 k x equilibrium squared, and I have kinetic energy. So at point D, I will have given up all of that gravitational potential energy, and the energy now will be partially stored in the spring and partially in kinetic energy. And this is the point of highest kinetic energy. So let's see how much that's going to be. So what we can do is, here I did calculate the potential. They probably didn't ask me, right? Yeah. So when they don't ask me, I did calculate the energy. Here is mg, h plus, the additional equilibrium compression of the spring. That says 384,000 joules. Now, at that point, the spring has acquired a potential energy, that's only about 1,000. So of the 300, we dropped this from a good height, right? How far was this dropped? 30 meters. That's like 10 stories, right? This is like a 10-story building. So you got a 10-story building, you got a 10-story elevator shaft, the elevator cable breaks, and the elevator drops 10 floors, and so, and then it hits this really stiff spring. I gotta go back and check numbers on this too. Check numbers and see, but what this is telling us right now is that this much gravitational potential energy, this much has gone into the spring. The remaining amount will be the 383,100 joules. So I can solve for the speed at point D. This should be our highest speed, to kinetic energy over m. It's a little faster. It's not a lot. So it didn't turn out to be much of an effect. When we first hit the spring, we were going 24.2. Now there's a little bit of rounding here too, so it would be interesting to see what the next digit is. But rounded to 3 significant figures. The speed when we first impacted, 24.2. And then we said, for a short distance, it continues to go up, and it goes up as high as 24.3. And then the effect of the spring is bigger than the gravitational force, and it begins to slow down. The acceleration has gone to 0 at that point. Now in D, it says at what point would the acceleration be the largest? And I'm hoping you're not thinking that the acceleration is the largest when the velocity is the largest, because that would be incorrect. The velocity is the largest when the acceleration is 0. The acceleration, it turns out, is going to be the largest when the velocity is 0, and here's why. What's going to happen is, once you hit the spring, mg is not going to change. So mg continues to exert a force downwards on the elevator, but the spring force gets bigger and bigger. As the spring compresses, the upward force due to the spring gets larger and larger. So when you first hit the spring, the acceleration effect is not so big, but as you compress the spring more and more, the force from the spring is getting bigger, and that means that the acceleration is getting larger. So it's not a constant, it is not a constant acceleration effect from the spring. The acceleration is getting bigger and bigger. Now the acceleration at any point, once we're in contact with the spring, is given by kx minus mg over m. Now the largest value of that acceleration will be where x has the largest value. So I can put in the maximum compression. So I'm going to put in the 3.06 meters in for x and solve. It says that the acceleration keeps going up once we make contact with the spring, and that it's going to max out at 202 meters per second squared. Now we dropped from 10 stories up, right? And what we're seeing here is the acceleration due to this spring, it goes up to 21 Gs. Now, I think at 21 Gs, if this spring was intended to be a safety device, it's certainly better than just hitting a concrete pad at the bottom of the elevator shaft. So it's a huge improvement over that. 21 Gs is still a pretty large acceleration. I think we need a softer spring. So we need to dig the elevator shaft a little deeper and put a bigger spring in there. Or, as you guys probably know, elevator shafts have these braking systems. Elevators have these braking systems. So if there's problems with the cable, there's redundant safety measures taken so that the elevator just locks in place until help can come. So I don't think they depend on a big spring at the bottom, but you know, it was an interesting idea to take a look at. So yeah, that you know, parts A and B were kind of a standard homework problem. C and D made that more difficult, right? There you had to stop and carefully think about what's going on. When would the velocity be the highest? When would the acceleration be the highest? And then carry out those calculations. So I'm gonna say that's fairly challenging. This one was fairly, it's kind of, yeah, maybe kind of medium, on the easy side of medium, difficult side of kind of easy side of medium, difficult side of medium, maybe just flat out difficult. Let's look at the last example and see how the rest of this exam went. So here we have a 1,200 kilogram car. It's 100, I don't recognize these units. What's a horsepower? A horsepower? That's a ridiculous unit. Have you guys heard of horsepower? Anyway, I looked this up. It turns out it's a unit of power, but it's really 746 watts. So I immediately switched this over. The car is 104,440 watts. So that's the power. Now, I always feel like what's important here, there's my force diagram that they wanted me to draw. Whenever we say there's you know, a certain amount of power, that power is associated with a force. What force is it? It's not the power of gravity. It's not the power of friction. This is the power of force F, which is the force. The engine's connected to a drivetrain and it's connected to the wheels, and it's the force that gets set up between the pavement and the contact point of the tires, and it's specifically the force pushing on the tires, pushing them up the hill. So we can take this much power and say this much power is going into force F. And on the diagram, there it is. It's a frictional force. The tires are turning. The engine is making sure that the tires continue to turn and set up that force with the pavement. And that's what makes the car accelerate. So now the other forces that were listed, well, we put in gravity. And again, I've got the mg cosine theta and mg sine theta components. There's the normal force. Now, there's what's called, what did they call it? This confused me a bit too. It's called it rolling friction. That's a funny way to state it. But typically in a problem, if you have something that says resistive forces or effective friction, this is calling it rolling friction. what that indicates is kind of all of the resistive effects of the car. Now what they did do is they gave us a coefficient. Anytime they give us a coefficient of friction, what that tells us to do is to take that coefficient, multiply it by the normal force, and use that as the effective frictional force. So we're going to go back and use our model that makes use of coefficients of friction. That's the plan. So for the friction, that's mu times n. Now from my diagram, I can see that n is going to be given in terms of magnitude. It's going to match mg cosine theta. So mu mg cosine theta, that's going to be my expression for the frictional force. Now it says in the problem, now this is kind of interesting, if we read it carefully, there's an incline of 5 degrees. Draw a diagram, we got that taken care of. What's the maximum speed at which the car is able to climb the hill? So what that says to me, I think what they're talking about, what they're getting at, is we're going to take that 104,440 watts. We're going to tap out the power of that engine, and we're just going to use all of that. And apply that for the force, and then that will enable us to go up the hill at some steady speed. So the idea here then is that the speed is constant. So v is constant, and that means the acceleration is 0. Now think about this. If you're climbing a hill, that's kind of what happens, right? You're in a car, you're climbing a hill, and at first you're able to accelerate, and then at some point, that's it. You know, you're going as fast as you can, the engine's just flat out at its top power, and so the way we handle that, I'm going to jump ahead to this equation, is that the power going into force F, I got the subscript here, I need to get the subscript here. The power going into force F can be written as F times V. So that says we can calculate the highest possible speed by taking the power sub F and divide it by F. So let's see how much force we're going to need in order to travel up the hill at a constant velocity. So if the velocity is constant, which is what we're saying here, then the F net will be equal to 0. The force of F needs to offset gravity and the frictional force. That's it. Those are the two opposing forces. Now the gravitation, because we're climbing a hill, mg sine theta, and then the resistive forces, the frictional and resistive forces, are being packaged into mu mg cosine theta. So I can calculate that. Everything has been given. I can put all the numbers in, and it works out that I am going to need a force, big F, coming from the engine and the drivetrain of 4,540 newtons. And I can take the total power, the 440 watts, divide through by that force, and that says at the highest speed I can go up this hill. That's a 5-degree incline. That's, you know, that's a good amount of steepness. But we can go up here at like 55 miles an hour. You know, it's coming up at 23 meters per second for the 104,000 watts. Okay, so which is not a huge amount of power, but we're still making it up the hill pretty well. It's a 1,200 kilogram car, so this is like my 2004 Honda Civic, something like that. And so I think the power is probably, maybe that's what it is. It's based on specifications for my 2004 Honda Civic. All right, let's see. Part C of the problem says the hill is 1,800 meters long. Calculate the energy transfers, the work, for each of the forces. So yeah, this is a combination of chapter 7 stuff, and chapter 8 is where we actually talked about power. But C is going back to chapter 7, and they're kind of related here. So the first thing, if they're going to ask me to list all the forces and how much energy is being transferred by each one, first thing I want to do is look at the displacement. What direction is the displacement in? Well, it's up the incline, so it's along the incline, tipped at angle theta. forces that are perpendicular are not transferring energy in or out. So I've got three possibilities here, I guess. Either a force or its component of a force is perpendicular. Those aren't transferring any energy. If it's in the direction of displacement, that's transferring energy in. If it's opposite the direction of displacement, that force is transferring energy out. Using that standard, what we can say is the normal force is not transferring any energy. It's perpendicular to displacement. And now here I've just taken components. mg cosine, the cosine theta component of gravity, that is also not transferring any energy in or out. Now force F is transferring energy in, right? And that, I hope, is fairly intuitive. So this force is going to transfer energy in, and the amount would just be F times D. And that worked out to be 8 million joules. So 8.17 million joules are transferred in during, now that's a good long distance, 1,800 meters. So that's that's a long distance that we're considering here. That's a little over a mile. A mile's like 1,600. All right. 8.17 million. Now, what happens to that energy? Well, I got to look at the other energy transfers. Gravity, mg sine theta, that's component of gravity, just the sine theta component, is transferring energy out. It's directed opposite to the displacement. And so there's a minus sign here, force times distance, and that turns out to be minus 1.84 million. So of the 8 million, 1.8 of those million are being taken out by gravity. Now gravity, we've learned, is a conservative force. That means that energy is still available as potential energy. And so this is going to be gravitational potential energy. If I turn the car around and go down the hill, I put the car in neutral, I can get that energy back. I can have that converted back into kinetic energy. So that energy is being conserved as mechanical energy. It is available. I've climbed to a higher elevation. Now the other force transferring energy out is friction. And that's, the frictional force times the distance. Now I put the minus sign in to show that the energy is being taken out. And this is the larger effect, at least in this example. The resistive forces are removing 6.3 million joules. So now that's typically going to become thermal energy. There are these techniques in cars now where you're trying to recover the energy from braking and such. This is a tough one. If these are just resistive forces, air resistance or friction within the operation of the car itself, that's probably just gone into thermal energy. That's not going to be recoverable as mechanical energy available. So anyway, running the numbers here, if we calculate all these W's together, they equal 0. Now for this problem, W net needs to be 0 because we're not picking up any speed. If W were a positive value, that would say by the time we're through the 1,800 meters, we have increased the speed of the car to a higher number. But we haven't in this example. So the W net is 0, the increase in kinetic energy is 0, all of the energy has been accounted for. Okay, so that's a good, challenging sort of problem too. If you guys have questions on that, let me know. Now we're through the first practice midterm set of problems. Go ahead and pause, take a break if you want. I'm just going to continue on. Here's another set of problems. So here we go. Another example of midterm 2 from some time in the past. 4 problems with parts A, B, C, and whatever. So the first one is a car rounding a banked curve. Now this is kind of similar to that first problem we had on the other exam, except this time the roadway is banked. It's banked at some angle theta, and that really complicates my force diagram. So I took a look at the car. See, I got the license plate this time, and the tail lights. That's my back view, and I've got a gravitational force. Now in this example, the direction of the acceleration is towards the center of the circular motion. And so the acceleration is in the horizontal radial direction. And so I don't want to use a rotated coordinate system. Typically we want the coordinate system to match up with the acceleration. Doesn't have to, but that typically makes the problems as easy as we can possibly make them. So I'm going to stick with a standard coordinate system, and that means mg is just fine. So mg is directed downwards, does not need to be divided into components. But the normal force has tipped, and in a standard coordinate system, that means I'm going to end up with a cosine theta component and a sine theta component. So I've got components of the normal force, both radial and vertical, and I got to make sure I get the sines and cosines correct. Any questions on that, stop off hours and let me know. The frictional force too. Now, the static frictional force could work in either direction. Usually I'm thinking in terms of if I'm going really fast, I'm going to need friction to help me make my way around the turn. And so what I did was I put the frictional force along the surface, perpendicular to the normal force, and so the frictional force will also have components to it. I'm going to have a cosine theta factor of friction component, and I'm going to have an F sine theta. So here are all the forces, and it looks like the acceleration will be a result of n sine theta, so the banking is helping, and the friction. Okay, if I'm going to go around this turn, I'm going to need forces in that direction. Now, there's actually, what they talk about in the problem is derive a formula that applies for when you're going as fast as you possibly can, and that's what we've done. But it also says, consider the case where you're going slow enough that you might need frictional forces to prevent you from slipping towards the center. Now this, at first you might think this is a little weird, but the curve is banked. And so if the car slows down, and now you're thinking, yeah, but there's going to be enough friction from the tires from that. What if it's been raining a lot? Or what if it's icy? You know, I'm going around a banked highway, and it's really icy, and the static friction coefficient has really dropped. There's a risk that if I go too slow, I will start to slide down the incline of the bank. I'll slide sideways, right? I'm driving this way, but I'm banked, and as a result, I'm slowing down, and I begin to slide towards the center. So for that, here's the plan. Once we get to that part of the problem, we will reverse the friction force. We'll reverse both components of friction. That'll work, and it's not a big deal. It turns out that we can typically do a problem all the way through, and then at the end we go, oh, what if the friction's in the opposite direction? We just change signs on the friction. So let's pay attention to that. All right, so here's the force diagram. The vertical direction says n cosine theta is equal to F sine theta plus mg. That's because there's no acceleration in the vertical direction. And in the radial direction, there is an acceleration. And that acceleration can be written in terms of net force and the mass. So n sine theta, along with friction cosine theta, divided by m, will determine what acceleration we have. Now, these two equations look kind of similar. What I'm going to do is I'm going to take the vertical and the radial equations. I'm going to take the lower one, the acceleration equation, write that as ma. Now, ignore these. I got some dividing signs going on, but for right now, just think ma can be written as n sine theta plus mu n cosine theta. Now, since we're working in terms, they gave us a coefficient of friction. Anytime we get this is the frictional force. So let's go back here. So there's a frictional force here. Since they gave us a coefficient of friction, and they're saying we're going to drive this right at the limit as to what's the highest we could travel for a particular static frictional coefficient, I can write that static friction force as mu times n. So That's handy because I can rewrite this as mu times n, and then I have a common factor of n. So I'll factor that out, and I have sine theta plus mu cosine theta, and that's all equal to ma. Now I can come to the second equation, and I can make it match. So I'm going to solve this for mg. Now if I solve this for mg, then the mg lines up with the ma. The mg would be given by n cosine theta minus f sine theta. I got to take that over to the other side. That's going to pick up a minus sign, minus mu n sine theta, factor out, common factor of n. I get cosine theta minus mu sine theta. Now I can take those two equations. I'm going to take the ma and divide by mg. The m's drop out. And then I'm going to take the expression in terms of the normal force, and the n's drop out, and it's kind of a miracle here. I get down to a over g is equal to this expression, sine theta plus mu cosine, cosine minus mu sine, and then I can solve this for v max. So the accelerations that we've solved for here are the highest accelerations possible. So we're going to take mu, we're going to have the frictional force right at the limit. V max for circular motion can be written as r a max square root. Making that substitution gives us the fastest speed we could travel would be given by rg square root. Square roots got dropped here. Okay, I've got to get those added in. So this needs a square root on it, and this needs a square root. It's one thing to forget to put the square root in my calculator, but I left it out of my formula. So that's going to need a square root, and that's going to need a square root. Now they didn't have us solve any numbers for this one, but in any case, I got to get that square root back in. So make sure you get that added in. I'll go back through the notes and get that updated. All right, let's see here. So that was the highest possible speed, and then the lowest possible speed, as we talked about, comes from taking the friction and reversing it. Now, how could I reverse the direction of friction? The friction forces are right here, but the friction force is represented by mu times n. So in these formulas, the terms that have mu, those are the frictional terms. And so what I can do is, where it was plus mu, I'll change it to minus mu. Where it was minus, I'll change it to plus. And what that has done is effectively that's reversed the direction of friction. So it would be interesting to put some numbers in and see what the maximum speed or the minimum speed might be for this example. Okay. All right, so that's a good problem. Okay, that's fairly challenging. Now there was an example, I think, in the homework that did something very, very similar. So this is kind of coming from that particular homework problem. All right, let's move on to problem 2 here. So we've got two planets that we're comparing here. We have planet Earth, and then we have planet Q, and they have different masses and they have different radiuses. It says that Earth is 10 times the mass of Q, and the radius of Earth is twice. This is going to be done entirely in ratios. So what we're going to do is, first of all, they ask about the gravitational fields. And so for the gravitational field comparison, let's give them by gm over r squared, gm over r squared. I can write that down for both, and then I can take g1 and divide it by g2. So I can take this expression and divide it. And here we can kind of see the power of using ratios. Because what's happening here is the big G's cancel out. And so the ratio of the gravitational field at the surfaces of these planets is going to be given by the ratio of the masses divided by the ratios of their radiuses. That's a factor of 10. This is a factor of 1/2 squared. It says that planet Q will have a gravitational field that is, now this got inverted, it's going to be 4/10 of Earth's gravitational field. Well, Earth's is 9.8, newtons per kilogram. So this planet would have a gravitational field of 3.92 newtons per kilogram. Now this problem, I'm going to say it shouldn't be that difficult, but the ratio thing, unless you've practiced it, can be a little tricky. So practice this problem, think about it. In part B, it's talking about gravitational escape velocity due to gravitational potential energies. And there we said we need enough kinetic energy to overcome the potential energy deficit. So the formula for that, for escape velocity, v squared 2gm over r. And what we can do is the same thing we did in part A. In part B, the formula is a little more complicated. We have some square roots here. But when we do the ratios here, the 2's cancel, the g's cancel, and the ratio of the escape velocities are going to be equal to the ratio of the masses, square rooted, times the ratio, inverse ratio of the radiuses, also square rooted. Now this time, the ratio works out to be 10 over 2 square rooted, and that's the square root of 1/5 when we invert it. Now Earth's escape velocity, we're told, is 11,200 meters per second. And so for this planet, it's going to be reduced by a factor of 0.447, so that's 5,010. So yeah, that's kind of a medium level. I know I moved through that one pretty quickly. I'm noticing that maybe we're running a bit behind schedule here. In any case, questions with these, practice using these ratios. They're really handy in problem solving. Those ratio examples are going to continue showing up. In problem 3 here, this is a potential energy. Now this is pretty similar to the elevator dropping. In fact, it's quite a bit easier, I think, than we had with that earlier example. Again, we have A, B, and C. We have the height, K value. This time we have the amount that the spring compressed. Remember before we had to solve for that, and that required a quadratic. So on part A, again, they're asking how fast are we traveling when we first make contact using potential energy at A equals kinetic energy at B. We end up with v squared is equal to 2gh. Put the numbers in, remember the square root. The speed here at impact, 8.52 meters per second. Now in the second part, they ask about how heavy is the block. Does that make sense? Let's see. If I drop the blocks, the speed that it picks up doesn't depend on the mass. But the amount of compression we get in the spring is going to, if I drop a heavier block, it's not going to be going any faster if we drop it from the same height, 3.7 meters, but it's going to, the more mass is going to require more force to slow it down, and so it will have an effect. What we can do then is we can make we can look at the potential energy in A and set it equal to the potential energy in C. So by the time the object, the block, has dropped all the way to picture C, where the spring is compressed and the block has come to a stop, that's going to be a drop of h plus x. So I can write the potential energy, mg h plus x, and then the spring energy, again, we're assuming an ideal spring, 1/2 kx squared. Now they wanted us to solve for mass, so taking this formula, the masses won't cancel out. This time, because we're working in terms of a spring, there's no m here, the mass doesn't cancel out. We can solve for mass. This is what the formula looks like. Put all the numbers in, check the units. It works out to be a mass of 11.5 kilograms, which seems reasonable. Again, check all these numbers, run them through, run through the numbers and the setup on your own, and take a look at these. These are not the problems on the midterm. I think I've mentioned that a few times before. They're just a set of problems that showed up on a midterm some number of years back. And so they do have the advantage of being something that has shown up on a midterm, but they're not the problems. They're good problems to work through. Think in terms of learning the principles. All right, let's get down to this last example. Now this problem turned out, when I put this on the exam, it turned out to be too difficult. And so I had to kind of scale this back a bit. But in any case, what I'm looking at here is, it says, let's launch a rocket to the sun. First of all, let's find out what point we have to get to. Where, between the Earth and the sun, at what location, would the gravitational fields cancel out? So for this, I drew a diagram. Here's point B. There's going to be some point where the gravitational fields cancel. Here's the gravitational field from the sun at that location, and here's the gravitational field from the Earth. Now the total distance, center to center, between the Earth and the sun is going to be little r, which is given here, the 150 million kilometers. And then I broke that up into the distance from the Earth out to point B, from the center of the Earth, and then the distance from the center of the sun out to point B. And what we ended up with is the distance from the sun divided by the distance of the Earth from this formula here. I can solve for it kind of in ratio form, is going to equal the mass of the sun divided by the mass of the Earth square rooted. I put those values in. Turns out that the distance from the sun is going to be 577 times as large as the distance from the Earth. So as you might imagine, the place where the gravitational fields match is going to be really much closer to the Earth than it is to the sun. So what I did was I said, okay, little r can be thought of as the distance to the sun plus the distance to the Earth. Now the distance to the sun is 577 Earth distances. That makes it 578 distances to the Earth. Putting that number in, I was able to come up with how far from the Earth is this location, and it's 260,000 kilometers. Now we can also go back and solve for r sub s, but you know, that's 150 million minus 260,000. That's just a drop in the bucket. So as far as distance from the sun, it's not going to really show up effectively in the numbers. So this is good enough. So 260,000 kilometers out. Now the moon is 384,000 kilometers away. So this distance where Earth and sun gravitational fields balance out is actually closer to us than the moon. Now in the second part of the problem, this is where the problem went out of control, it says this. It says, what would be the minimum launch speed needed for a rocket leaving Earth to reach the sun? And the reasoning here is we don't really have to escape totally Earth's gravitational potential energy. We just have to get to that point we identified in problem, in the earlier part of the problem, in part A. If we can get back out to point B, then from here the force from the sun will be larger, and so we can coast. In fact, the problem we're going to have if we do this is we're going to be going really fast when we get to where the sun is located. Now I'm going to go through the setup pretty quickly. You're not responsible for doing a problem of this difficulty. At the time I gave the exam, I had to, students didn't end up doing this entire problem. So I think I have eliminated part C, and because once I was, at some point I realized it was really too challenging. But basically we can start at point A, include potential energy from the Earth and the sun, and then compare that with point B, where we have potential energy due to the Earth and the sun. So I've got a bunch of these GMM over distance terms for the Earth, for the sun, for the Earth, for the sun. The tricky part is getting all the distances correct. So again, I'm going to let you guys go through this. If you have questions, stop by office hours. But I carried through all the algebra so you could see how this might work. And at the end, what I found was there was a small effect in terms of the kinetic energy. So Let me just show you some of the results, and then we'll wrap this up. Keeping track of the effect of the sun pulling on the spacecraft. Now, before, when we solved for escape velocity from Earth, it said we had to travel 11,200 meters per second. Well, to get to this balance point between the Earth and the sun, it wasn't so very different. It worked out to be 11,070. So, you know, it's a little easier. We don't quite have to go as fast because at some point, well, all the way along, the Earth's gravitational effect will be pulling us towards the sun. So anyway, that's what it worked out to be. I'm going to say, you know, follow those first few steps through the problem. Certainly part A is doable. Don't worry so much about part B unless you're really interested in seeing how a more complicated problem would come together. Now for part C, it says if we do this, what speed will the rocket hit the sun? When I did this in great detail, I found out that extra boost didn't make all that much difference. And so here I just solved for the escape velocity from the surface of the sun. So escape velocity from the surface of the sun works out to be 619,000 meters per second. That is really, really super fast. So those particles, you know, the solar flares and stuff coming off that successfully make their way away from the sun, they've got to be going at least that fast. Otherwise, gravitationally, they're going to get, that material is going to get pulled back into the sun. Okay, so that would be an escape velocity. Now you're thinking, wait a minute, escape velocity, didn't the problem ask about impact velocity if we drop something? And the response to that is, yeah, it's the same thing. So the escape velocity that it would take to launch something so that it's going fast enough that it never slows down completely and returns. That's the same thing as starting with something out far, far away from the sun, basically at infinity, and letting go and finding out what speed it returns at. So the escape velocity would be sending the object out to infinity, and the impact velocity on the return would be dropping something from infinity, and that's what it worked out to be. Okay, so yeah, I apologize, I'm sorry that I did leave this in place just to show you that, you know, sometimes these things come up. If you're on a problem and it seems like it's kind of too extreme, let me know. This one I'm pretty sure, if I remember, I caught it before giving the exam, but I left it in for the review. It was kind of an interesting example to take a look at some gravitational potential energy calculations. All right, I will leave it at that. Keep, you know, reviewing, preparing for midterm 2. If you guys have any questions, I've got a bunch of office hours. Stop by and we will look at whatever questions you have.